Hello, Mr. N-ary, Mr. Ryan, how are you today?
Good.
What's this?
Binary tree.
Binary tree. What's the depth of it? What's the depth of it?
1, 2. Oh, no, 1, 3, 4.
Depth.
1.
2, 3,
3,
3. 3 levels. 3. Why is the 4? Why is 4? Okay. Go back. So the binary trees are kind of graph, right? And for binary tree for each node has at most 2 kids, and for each node it has only have 1 parent, and which node does not have parent, and what do we call it?
Root.
Root doesn't have a parent, and the nodes which don't have these children we call it leaves or terminal nodes. Okay, that's easy. So previously we talked about this depth search, breadth search to count the depths. Yeah. So do you still remember? So first of all, the binary tree. Let's write this binary tree definition. Class tree. Define the constructor in it. So we will have what? We will have a value, and then we will have a left equals none, and right equals none. Right? So this is basic definition of binary tree node. Okay, and then self, we can say self dot value equals value. So look, this is value here, yeah, and self dot left node, where it points to. Yeah, it points to a left, and it points to a right, right? And it could be none at the beginning. It could be none. Yeah, so points to left, and then self dot right equals right, and then this is this. Okay, so that is the object. That's the class tree, object-oriented programming. We talk about that. Yeah, it has 3 properties: value, left, and right. So with this definition, we can easily do this depth search easier. So define. We want to get a depth, max depth. Yeah, depth root with the root. Okay, so if not root, we return 0. Yeah, for the empty node, it has 0. Very easy. And now we just need to return the maximum of what? Depth root of right, root of left, yeah? Yeah, recursively root of left, and depth root of what? Huh?
Right.
Right, easy. Look at the tree, the root of left, root of right, plus 1, right? Because look, if you have a tree, if you know this tree, the left, it's for example like 3, and you plus 1, that's the depth. And then if there is right, if this is 4, plus 1 is 5. So we are recursively, we call this recursion, and this is the same function recursion, to solve this problem with a smaller size, yeah, root of left, and then plus 1, because we have to plus 1, the root node. Make sense? Huh? And all we can do, use the breadth search, yeah, to push the node, to visit the node. What's the breadth search of this order?
1, 2, 3, 4, 5.
Yeah, level by level, and we use the queue, right? We use the queue, double-ended queue. Remember, we use this. This is append. We append the root first, and then we take the node. Every time we take it out, we push its kid back to the queue, right? And for each node, we have to append. We can take everything out of the queue and then append their children. So in this case, we can guarantee that all the nodes in the queue belongs to the same level. For example, like look. Okay, this one, yeah. First of all, I put the 1 in, right? That's the initial root. I take it out, take everything in the queue out. I push the kids, which is 2 and 3. Because look, 2 and 3 are belong to the same level, yeah. Or I can take everything out, 2, 3, and push its kids, 5, 6, 4, 5, yeah. 5, 6, 4, 5. So look, at the same time, at any time, the nodes in the queue belongs to the same level, right? Alright? So in this case, we can have just single variable to increment the depth. When every time we take everything out of the queue, we have a variable. Alternatively, when we push the node in the queue, we can also remember the depth at a time. For example, if instead we put a topper 1 and 0, right? And then we take it off, we put a kid 2 and 3, but 2 with the 1, the level 0 plus 1 is 2, 1, and then 3, 1, right? So we have a tuple. The second value in the tuple is the level. The first value is the node. Right? Okay, so let's just a little review. We have talked about this previously. So today's task, we talk about these similar, but we are not talking about a binary tree. We're talking about N-ary tree. So what's N-ary tree? Is that
It has more than
two kids?
kids.
Easy, yeah. One, it could be 2, 3, 4, 5, right? Something like that. And then it could be 6, 7, yeah, up to maximum. You know, it doesn't have to be. There's no fixed number. Yeah? It could be a list of the children. So let's define this first. Class tree. This is the same. And then define init. This is the reserved constructor function. Means that whenever we create a tree node, this function will be called constructor. We call it initializer. Okay, init. So self. And then we have a value, of course, and then we have a children. We just have a children. Children, okay. Children equals at the beginning is the list of nothing, okay. Or you can put it none. That's a list. This is a list. Yeah, list of nodes. List of trees, tree nodes, okay. Tree node, for example, tree node. And then this is the same, yeah. Self dot value equals value. Self dot children equals children. Okay, this is the template. A template for us to create a tree with the N-ary tree. N-ary tree. Okay, N-ary tree. So it's simple. We want to get the maximum depth. Yeah. So what's your approach? Come on. Is it the same as the binary tree? Can we apply the same algorithm to in this?
Yeah.
Yeah, of course. Depth search, breadth search, right? Easy. But instead of left and right, we need to visit this. This is the list of children. We just have to go through the list of children. Okay. Let me write it. Okay, it should be very easy.
And then
Depth search, breadth search. Let's try with the depth search first. Okay. Try with the depth search. With the depth search, usually we implement with singular recursion, right? So with the recursion, we don't have to worry about maintaining the stack, because the computer just maintains the stack for us, and we can just. With the recursion, it's easier for us to implement it. It's usually a most intuitive way, right? Because we just call, okay, we want to get the depth of the left, for example, like binary tree, left subtree, and then we're going to get the depth of the right subtree, and we can just recursively call it because it's already defined, right? Define depth, and then this is the root, okay? So at the beginning it's the same. We want to check if it's empty, right? If it's empty, we return what?
nothing.
Okay. If not root or if root is none, okay?
List.
Yeah. Look, if root is none, or if not or not root, it's the same thing, okay? Return 0, yeah. Return 0 because we will get the depth, yeah. And now we want to visit the kid is children, right? Yeah, this is children has the list of this is the list of nodes. Yeah, list of nodes. It's the list of tree node. Yeah, tree node. This is the type of list of tree node. So answer equals 0. Now we just need to go through for kid. Let's say for kid. Yeah, for kid in root of what? For kid in root of what?
Up.
Huh?
Oh no.
Children. Come on.
Children.
And then we want to, now what's next? We have the kid, and then we want to do what? We don't call this function recursively to get the depth, yeah? Alright? What's the depth of a kid?
Depth.
Depth kid, yeah? So now we want to compare it, yeah? So answer equals max answer depth kid, yeah? Easy, yeah? And then return what? Answer plus what?
Equals.
Answer plus what? Plus return answer. Look, we have a node. Yeah, this is a few nodes. This is the kid. Yeah, this is a kid. Load of kid. Load of children. List of kid. And then we get the nodes. Yeah, plus 1 because we have to add these. Got it? Yeah. Make sense, Ryan? Are you with me? Yeah. Okay, so this we can turn this into one line. Yeah, into one line. We can just say. We can just say what?
Oh yeah.
Return. Okay, this is one line. We can return max. We can use this max function. Okay, okay. Max what? Depth I for I in root dot children, right? Yeah, you see? And then we need to give it a default. This parameter default 0, yeah. Why we need to put it default like that? And then plus 1, right? This is the same thing. Max function, look. What's max function? This is the Python inbuilt function. Max 1, 2, 3. What's the value?
Sorry.
Yeah, easy, yeah. And if you give a max nothing, you will complain, you'll scream, the computer will scream. So if you give that nothing, yeah, a list of nothing, you will scream. You will say, okay, this is not what I want. But you can put the second parameter default equals 0. Then this is okay, right? Because look at it, if this is none, if the children, look, if root of children is none, terminal node, the leaf node, I need return 0 here. If you don't give a return default 0, the computer says, okay, I don't know what to do. Make sense? Because you're asking me to compute the maximum of nothing. What's maximum? If you compute the maximum, it has to compare, right? One number. What's the maximum? 1. What's the maximum? 1, 2, 2. What's the maximum of nothing? I don't know, but you need to tell me default.
Maximum of nothing is nothing.
Yeah, but you have to say default equals 0, okay? So let's guess. And then plus 1, we have to plus 1. Okay, so let's start DFS search. Easy, yeah? Okay, let's talk about breakfast search. And that will be it. For the breakfast search, we can keep these, yeah? Obviously, right? So breakfast search, we use the queue, obviously, yeah? We use the queue, double ND queue. Q equal DQ. So at the beginning, we want to push what into the queue? We want to push the what in the queue?
Children.
No. What children? At the beginning, for the queue, to implement a breakfast search, at the beginning, we need to put something into it. We need to put something into the queue. Root.
I literally said root.
Okay, you said children. I didn't hear you. Okay,
I said
root.
children and then I said root.
Okay, but you have to be more confident. Root. So at the beginning, if we put a single root, right? Then every time we need to take everything out of root. Okay. Okay. So now we have this answer at the beginning is 0, and then while q, then what we need to do? Every time we take a nodes out of q, we need to increment the answer, the level, right? Make sense? Look. 1, 2, 3, 4, 5, 6. What's the breakfast search order of this? Come on, that's easy for
1,
you.
2, 3, 4, 5, 6.
Easy, yeah. But how do we emulate it? This is a queue. At the beginning, we put a 1 here, right? 1 here. The answer will be 0 and then here. Okay, answer will be 0. Then we take it out. We take everything out. We increment it to 1. And we push its kit. The kit of 1 is 2, 3, 4. We push it in. Okay? And now every time we take it out, look, we take 2, 3, 4 out. Everything in the queue out. We need to increment the answer. What's the kit? What's the children of 2, 3, and 4?
5, 6.
5, 6. Because these two does not have kit. And then we take this 5, 6. Yeah, and then we take everything out and push it, keep it. It has nothing. Okay, so the answer is 3. So that's it. So YQ then answer plus equal 1. Yeah, as I just said. And I need to take everything out. So how many kids are there in the queue? Which is length Q, right? And I have just to say 4 in range N. I take it out. Current equals Q dot pop what? Pop left or pop right?
Pop left.
Pop left, yes. Pop left. We want to take it out from the left
Pop
side.
at the right.
There is no pop right. Well done. It's pop. Okay. Pop is pop right. Pop left is pop left. Okay. Make sense? And we take it out, right? We take it out. Then what do we need to do? We need to push it to kid. Yeah. For kid. In root dot children. And then we just say q dot append kid. That's it. You notice that the breakfast search and DFS search for the tree is much easier than the graph. Remember a few days ago we talked about the DFS search and breakfast search about graph. right? Because the graph is bidirectional. So look, if you travel from 1 to 2, the binary tree, you can't go back, right? Or the trees, there is no way for you to go back. But for the graph, if this is the dimensional graph, then if you visit from 1 to 2, and the next time you may travel back, and there will be cycle. That's why we need to use the hash set to remember the nodes, right? The vertex, so we don't visit it again. But for the trees, it's easier. We don't need to define such thing, right? Well, we can just follow the children, and then you will go from the root to the kids until it hits the terminal node, which is the diff node, and then we just return answer. Yeah, return answer. That will be it. So I was also talking about there's another way of writing this breadth search, which is to append the node and its level at a time, right? At a time. So instead of pushing the single root, I push a tuple. So which is at the beginning the root is 1. Okay. Yeah. So now I don't need to write this answer, right? I don't need to. Actually, answer is 0. Let's say. Answer equals 0, okay? And then
you're writing on wet.
Yeah.
It will rub out some of the.
So instead of taking n nodes at a time, I take one node. I always take one node. Yeah, I take one node. So I say current and the depth d equals q dot pop left, right? And I have these steps, then I can say answer equals max answer d, right? And then I don't need to. I just need to. Oh yeah, I just need to do this for kid in. Okay, so previously this is not root. Okay, this is current. Okay, current. Yeah. For kid in current or children. Okay. Previously the one is current, not root. Okay, I put a mistake there. For kid in current or children, and I obtain kid. Kid, that's a tuple, and I put a second variable, which is the d plus 1, right? Because the current depth is d, and then I push it to kids, the level will be d plus 1. Make sense? Yeah? That's a tuple. And then next time I take one node out, and I compare with the maximum answer. So in this case, I will get the maximum depth. So in all the cases, yeah, depth search and breadth search, the time complexity is what? If there are n nodes in the tree. N, yeah. What's the space complexity?
N.
N, yeah, because we're using the queue, right? And then for recursion, we're using the stack, right? Okay. Yeah. So look, to sum up, this is quite similar to the getting the maximum depth of the binary tree. The only difference is the children. Yeah? Instead of 2 left and right, we need to get it from the list of children. And for the recursion, we're using for the depth search, we're using recursions to compute the maximum depth of each child, each kid. Yeah, and the maximum the depth of this entire tree is the maximum depth of each kid plus 1, yeah, because it comes from the current children, okay? And then for the breadth search, we just expand it level by level. Okay, that's it for today. Good job. Bye bye. Bye bye.